Hello. What we have set up today here is a Q-block control system that is controlling a sure stepper motor. And so I'll break down each individual component here, and then we can talk about how the whole system functions together. So firstly, we have a sure stepper motor right under this dial here, which looks very similar to this piece here. We've got a stepper motor that has 1.8% resolution, and it's 2.5 amps. And then next to it is the sure step driver, which is kind of a pathway of the voltage that is being supplied to the stepper motor. The stepper motor is a two-phase motor, and because of that, it has four conductors that are going to the driver, each one of those having a positive and negative control that supplies the voltage to the driver, from the driver to the motor. And next to it here, we have an inline fuse that is typically not called for because in a normal setup here, the sure step actually has a proprietary power supply that will protect that. But I don't have one inside the system, so the manual called for just putting a 4 amp fast flow fuse in line. So I have that there. And then we come to the Q-block study board, which is a learning tool made by Q-block, which is a PLC, a programmable logic controller. And what it allows me to do is set up pathways and exert a certain amount of control on my system, depending on the programming, which is in Q-block Studio here. It has certain lines of code which are all complicated and can be learned through the manual here. But what this allows me to do is through a series of I/O ports, I can set up commands so that, for example, when I get an input command of one of my switches a button moving, it can then output a certain signal as well, controlling my stepper motor. Let's see. So let's look a little bit closer at this Q-block here, where all these patch cables are. And all of the red cables are going to be my inputs. So this is all controlling the push buttons here, as well as one of these switches. So I'm going to go ahead and run my, sorry. The white conductors here are controlling the outputs that go to the driver, which are then filtered, I guess you can say, and then supplied to the motor. So I'll just show you an example of the experiment that I set up using this degree wheel, and I've actually taken a little piece of copper conductor here and aligned it in degrees around a circle. So it goes all the way from 0 to 360 degrees, and it's divided 90, 180, 270, and then all the 45s as well. So what I've programmed these buttons to do is provide a varying level of frequency and pulses to control how far the stepper motor is going to rotate in order to kind of get it to a specific location that I want. There's several applications that this could be used in a variety of like industrial settings if you need to get a motor queued up to a certain place before it starts, or if you need something to be in a very particular position. You can control the pulses and the frequency to get that motor to where you need it to be. So I programmed these first 5 switches to do a variety of rotations, the first one being 360 degrees. So it just rotated all the way around and stopped at that point. The next one is 180. So it rotated roughly 180 degrees. The next one is 90 degrees, another quarter, 45 and then another 45 to set it. It's a little off. There's some fine tuning that could happen, but you have complete control of that within the coding of this in the Qblox Studio. Another thing I did is I wanted to be able to reverse the polarity and have the motor rotate in another direction. So what I did is on one of these switches here, I put the polarity, essentially when it's down, it's forward, and when the switch is up, it's reverse. So going back here, I'll show that it is now reversing the direction. And I have not set it up in this experiment, but you could very easily set up any of these potentiometers to vary the speed or continual rotation if you wanted to go that far. It's just a further example of how you can use programmable logic controllers to provide low voltage signals from computer software to hardware, and then how you can set up your pathways of control with switches, potentiometers, push buttons, everything like that to control stepper motors. And that's pretty much it for this experiment. Thank you.
Wow.
My name is Daniel Barnhart, and I'm going to talk to you about the project that we worked on this semester. What we have here is we have a Dayton 1/4 horsepower dual voltage motor. It's configurable for 208 to 230 volts or 460 volts, three-phase. And we're using an Automation Direct GS2 variable frequency drive to control it. What I want to talk with you about today is this drive right here can use pulse width modulation in order to control the speed of this motor. Pulse width modulation is a process where this controller takes AC voltage, converts it to DC voltage, and then back to a simulated AC voltage. This graph right here kind of represents the way that it does that. This is a standard sine wave right here. You've got one full cycle that it's showing here. You got a half cycle here and then a negative half cycle here. And what the pulse width modulation does is, instead of varying the amplitude of the signal, it actually it has full amplitude but varies the length of time that it actually applies that voltage to the motor. The advantage of being able to do that is that it allows for full torque at a slower speed. The way that it does this is it uses the two main components that it uses are a series of diodes and a series of transistors called IGBT transistors, which are insulated gate bipolar transistors. What it does is it uses the diodes to convert the AC to DC first, and then it sends it through the transistors. It sends a full DC signal to it. The transistors act as switches. The switches open and close, and that's what creates the pulsation that you get right here. So let's give you a little quick demonstration here. So right here we have approximately 60 hertz. And what this is doing is this is showing an averaged voltage level to the motor. And if I were to turn it up, the motor spins faster. The average level of voltage that the motor sees increases, and it increases the speed. So that's about it. Thank you very much.
Hi, my name is Matt Falcone. I'm going to go through a forward and reverse control circuit for a motor. Over here I have a non-energized display of what we're going to be talking about here. Over here I have a 120 volt to 24 volt transformer, and what this is doing is making sure that we have a lower voltage going to the controls, so the operator is not pushing a button that is controlled with a 208 volt circuit. So it's for safety than anything else. So this is taking 120 volts in single phase for the control circuit down to 24 volts. And it runs through some push buttons, and the push buttons then are connected to this contactor. And this contactor is set up in forward and reverse. We have here an interlock, which keeps the contactor from being able to run in both forward and reverse at the same time. So if you're pushing down this one won't push, and same with the other way. It won't energize both sides of the circuit at the same time. A contactor is kind of like a relay. It has a coil in it, and when you energize the coil with your control circuit, what happens with the coil is it creates a magnetic field and then pulls these plungers down, then energizing, allowing electricity to flow through your contactor from your 208 volt source. This is your overload. Your overload is your safety device. It helps protect the motor in case of excess current, short circuit, excess heat, single phasing, any of those situations. This will open the circuit, cut off power to the motor, protecting the motor from damage. This is a timing relay. What this relay is here for is to allow the motor time to slow down and stop before you're able to engage the different directions. So if you're going forward and then turn off power to that circuit, so because you want to stop it and run it reverse, this is actually set for 10 seconds to allow that motor time to slow down and stop before you're able to re-engage the other direction. It'll damage the motor if you run it forward and reverse at the same time. So the motor over here, this is the motor that I'm running, and this is my functioning forward and reverse. I have a stop button, forward button, reverse button. I have LEDs installed in here to indicate which direction the motor is going into. So if you push the forward button, it is now currently going in the forward direction. And as you can see, pushing the reverse, the interlock is keeping it from engaging in the opposite direction. You have to push the stop button, and you have to wait 10 seconds for the motor to slow down and stop. You can see I can't engage the engine of the motor. And again, the other way, I can't engage it in the opposite direction while it's running. That's my forward and reverse.
Thank you.
Hi, I'm Robert Demery, and I'm going to talk about frequency drives. They're a variable frequency drive. It's a type of motor controller that drives electric motors to vary the frequency and voltage supplied to the motor. This is a frequency drive. It's a GS2 model. This is our motor that we're running, and it's a three-phase motor. And here's a little picture of kind of how it's wired up, going into the motor and going from our power source. I'll show you how to set it up. Set it up, there's a bunch of program buttons, and it's run off 208 volts. Set it at 1.5 amps, 60 hertz. The minimum RPMs, we're going to go to 25 because that's what the motor's rated for. And we'll just set our max to, let's say, 2,500 if I can get there. Right there. All right. Now, we hit run, and we control this and hit display. As we turn up frequency, it'll show you what our hertz are. And now we have 86.9 hertz. As you change the RPMs, you can see that. Alright. Okay. Our amps will change as the RPMs go up or down. So the faster the motor's going, the less amps we're going to have. The slower it goes, the more amps. And you can also switch it to reverse. Whenever it slows down, switch to reverse. And now it's running in reverse. Alright, now I'm going to talk about the braking. There's two basic types of braking systems. There's dynamic and regenerated. The regenerated is pretty much what is mostly used. It permits the energy to the feedback in the power system. It's most commonly used in automobiles, hybrid engines, and it just keeps the power from being delivered back to the battery when the brakes are applied. And that's it.
All right, I'm Brian Lilly. I'm going to be talking about the magic of what's known as a variable frequency drive or inverter drive. As the name implies, it varies the frequency going to something. Usually these are used for motors. The frequency, the ability to vary that frequency allows us to change the speed of a motor and possibly the torque, and gives us some good controls over how we operate motors. But the variable frequency drive has a lot more capabilities to it that are kind of lost in the name because we just focus on that frequency change. A high-level view of how it works: we've got incoming power from a utility or from our building. It's going to be fused coming into the drive. The drive converts that AC power coming in to a DC power. The drive itself all operates off of DC. It converts that back into a DC or AC pulse width modulated power coming out to your motor, and that's where the inversion part comes from. Varies that frequency and allows us to control that motor at different speeds. So the control part of it is where it gets lost. It's actually multifunction in this drive. It can act sort of as a PLC. It takes the place of many components like contactors and relays, timer switches. All that can be incorporated into the drive. You have multiple inputs. This one has 6 different inputs that you can put into it. They're completely configurable. They can do different things depending on what you want. The list isn't endless within the drive, but there's many functions like controlling speed, fault conditions, start-stop, just a lot of different things you can do with just simple switches inputting into these, what's known as a digital input of the drive. You can also externally control the speed or the frequency output with an analog signal coming in. That can be done with an external PLC, computer controls. It can be done with a potentiometer where you would just turn it. It can be done with analog current signals. So a lot of different options to cause this drive to vary the speed. Another part of the drive is that it has outputs. So you have inputs that can come into it and it can make decisions based on those inputs. It's also got outputs that can come out and tell you things about the drive. You can set them up as fault conditions, or you can set them up as run conditions. You can set them up to read when you're at speed. You would use these maybe for turning lights on and off, for indications that you're running forward reverse, or that you're at the speed that you desire to be at. So a lot of functionality there. It's also got analog outputs that's usually used for indicating speed or frequency out to an external device. So a lot of different ways you can control it. Down here you can see it's also got a serial communications port. So you can hook this up directly to a computer, use computer software and control all these different functions, get feedbacks, get all the information. So it's a really versatile device that not only varies frequency and simply lets you change the speed of the motor, but has a lot of different functionality. Step over here, we'll talk about the display just a little bit. Along with all the inputs and outputs that you can get, it also has a lot of just meters and displays to let you know what you're actually getting with your motor. It's going to display your frequency, so that's what your frequency is set at. It will convert that for you and display the RPMs. If you're scaling the frequency for some reason, it shows you that scale version. You've got a meter for your current, the percent load that's being put on the motor, the voltage, PID set points, which is just another complete function that we haven't even discussed, and we'll leave that out because it's complicated. And then basically you go back to your set point frequency. We skip those three and it'll display. So you can see there's a lot of meters built into this too, so you don't have to have external meters and things. You can come up and get some basic information about your motor and controls. So now we kind of have a real high level view of how they work. See this setup here. We've got the variable frequency drive, the motor control, the input power coming in with breakers and fuses, and we have a switch set up. What we did on this guy is we've got a latching start and stop. We've got a forward and reverse control. We've got 3 different speeds that we can control on this drive, and we've got a magic boost button, which is pretty cool. So in the first speed, we'll go ahead and start this guy up. You can see it. We've got it set to run pretty slow. This first selector also allows me to use my control for speed on the front panel. So I can vary that, and I've set it up for every speed that I've got a little boost. So we're running at about 15 hertz here. I hit that and we've doubled it to 30. Run a second speed, same thing. We can double speed. And those buttons can be set up. They're based on the digital input and how you program inside the drive itself. You can make those do an infinite number of different speeds and different functions. The drive also can reverse. With the variable frequency drive, it knows how to stop the motor correctly in reverse, so you don't even have to stop and restart. You can go directly to reverse and it will reverse. And then I have all the same functionality. I can run the different speeds. I can run my third set point on every one. And I have a nice little stop button. So you can see it's just a lot of configuration and just powerful device that the variable frequency drive is. Thank you.
My name is Uriel Lopez, and today I'm going to be talking about forward and reverse, my project forward and reverse. The things that I used for my project was two set of contactors, interlock, overload, transformer, and a timer relay. The interlock is the heart of the whole project. This is a mechanical interlock that keeps one contactor off while the other one is running. And it does this by these mechanical things. As one is on, it don't let the other one go on. They don't let the other contact energize. And on the interlock, you got normally closed terminals, which on your contactors, all you have is normally open set of terminals. And the voltage that I used was 120 volts, 24 volts, and the 240 volts that come from our breaker. on the on the project, I have a timer relay that that doesn't let the motor runs that lets that the timer relay lets the motor speed down and give it a complete stop before pressing the button again. And I put it in front of the transformer. The reason that I put the timer relay in front of the transformer is because I wanted the motor to stop completely when I press the stop button for the forward when it's going in forward mode, and when it's on reverse. So I stop it and I have to wait for my 10 seconds, and then I can press the buttons. As you can see, I got my stop button in front of the transformer because I wanted everything to turn off when I press the stop button. The transformer is kind of controlling the whole thing. And then right here, once we go to our 24 volts, I got a wire going in from the timer relay, which is on terminal 9 and 5, and it's making a holding contact for my buttons, which is my two green buttons are running on 24 volts, and the holding contact is so that when you press the button, it stays on, it won't turn off. And the interlock is the one that's sending the power to my coils on my forward contact and my reverse contact. And then we got a device that is overload. Overload is made to protect your motor. The overload detects heat and it can detect high current, and it's normally wired up on your neutral side of the project. So that's that, and I got a 3-pole breaker, 30 amp, that feeds directly to my terminals on my contactors. And this for my contactors will always have power even if I don't press the button, because the contactors are fed from this 30 amp breaker right here that goes straight to the terminals. So my overload is connected to both of my contactors, even though it's just connected. It's just placed inside. It's just placed on my forward, but it's controlling both forward and reverse contacts. This is my overload, and the way it's protecting both contactors is because, as you can see right here, my forward contactor and my reverse contacts are jumped. They are jumped so that it can go straight to the overload. And when I was doing the project, I noticed that that we have a unbalanced load on the B phase of the panel, and the reason why we have unbalanced load is because the relay, the timer relay is on a 15 amp breaker, which is ran off on the B phase. That's why it's an unbalance on the middle side of my thing. But I can show you that the thing is unbalanced. See, on A phase, it got 66. I don't know if you can see, it got 65 amps on it. On my middle, on my B phase, I got 78 amps. B phase, I got 65 amps. So that's telling me that this is pulling more amps. But the reason is because my 50 amp breaker is on the B phase. And that's it. Thank you.
My name is Keith Pearl, and today I'm going to be talking about variable frequency drives, which is this right here. Everything's operating on 208, which is this motor, this, and the disconnect. The way a variable frequency drive works is it varies the torque and speed of a motor by the voltage coming in, and also by the frequency. And what it does is it takes the 208 volts going in here, runs it straight into the frequency drive. It drops it down from AC to DC to run everything internally. And then before it comes back out to the motor, it converts it back into AC. So basically what it does is it takes the frequency and it can raise it or lower it to control the speed of the motor instead of changing the amperage. And one thing that surprised me during the project was during normal function, normal operation to like 60 hertz, that's standard, which is right approximately right there is standard operation. And then whenever you turn it up, double the frequency, you would think the amperage would also double. But as you can see right here, the amperage lowers as the frequency rises. Here, it's at about half an amp, and then when you go back to standard operation, check the amperage, it doubles. So it's a 0.9 now. And that's about it.
Hello, my name is Daniel Watts, and I'm going to be talking about relays. So relays are basically an electrical switch that can be turned on or off. They work by having a coil, and once the coil is energized, it uses contactors, normally open and normally closed. The normally open become closed once the coil is energized, and the normally closed become open when the coil is energized. On the ice cube relay, which is this, 9 through 12 are the commons, meaning that power is supplied to them. If power is supplied to 9 and the coil is energized, then there will be contact between 9 and 5. The timing relay follows a similar format. 14 and 13 are the coil, 9 and 12 are the commons, 5 and 8 are the normally open, and 1 and 4 are the normally closed. So right here we have a ladder diagram for this timing loop circuit that I have. And so power is supplied to 10, 9, 11, 12, and 8 on each of the different contactors. And what it will do is power will be fed here, and power flows through the project, and then it shuts off and then cuts back on through the timing relay. Typical applications of this are security and automation, and in the other project, timing relays are used, so the motor has to stop before you can start it again. Yes, I'll put it in. As you can see, the green light's powered, and for a brief second, the red one will be powered, showing that the contactors switch momentarily. You can see this one shuts off for a second. Yeah, that's it.
Good morning. I'm Charles McDaniel. Today we're going to talk about a little bit of the industry that I've given over 27 years to. This is the textile industry. This particular type machine is a Vanguard knitting machine. It's manufactured in Monroe, North Carolina. It produces t-shirt fabric. In this industry where these machines would be located inside a factory, safety is always a priority when hands, arms, legs, or person is in and around the machine. So today I have designed and set up a circuit that's going to demonstrate old technology and new technology, the gate safety circuit and the run circuit. This machine also has to have the capability to adapt to many different locations, which the power supplies in many countries are different. In Mexico it's 220, in Montreal, Canada it's 600 volts. The southern US is 575 volts, and here in North Carolina we use 480. This machine has to have the capability to use a transformer to utilize these settings. The variable frequency drive we're going to talk about today is also a great asset to this, because it can allow a technician to set this machine up at a break-in speed, which would be at a low speed, and then later after the machine is broken in, we can speed the machine up. So here is a schematic of what I have done today, given an idea of how we're going to do a start, stop, and a jog. Also, we're going to do the main safety circuit itself and display an amber safety light showing that we have energy on the circuit but no power to the circuit. So we'll demonstrate that now. And as we can see, our 220, 208 incoming power, three-phase power, has now energized our safety circuit. We now are illuminated our amber light, but we have no power to the rest of the circuit. So if this were in the setup on the machine, it would tell an operator or a technician the machine does have power, but it can't be energized or turned until you reset. When you reset, you send power out to the circuit, to the frequency drive, and to the control circuit. The frequency drive will receive 208 three-phase. The motor we're using today for the demonstration is a Dayton. It is a three-phase 208 460. Today we are using 208 to drive the motor. We have it set up with the frequency drive to run an RPM of 1750. We're going to demonstrate that now. We're using a on-off click start switch, and we will eliminate that with the green LED. Bring that up to 1750 at 60 hertz. Once we receive that, this will be the machine at full speed. If for some reason the machine stopped or we need to stop, we have changed the settings and parameters in the frequency drive to decel, and we have set that at 1 second. So when we stop at 1 second. And also lets the operator know by illuminating the red LED. Now, periodically there'll be times when the machine needs a repair, and you need to do nothing but jog the machine from one location to another. So if that's to be done, the operator or technician will just simply come over and mass jog, and we can turn the machine at a much slower speed. And again, if for some reason the gate is open, the gate on this machine would have a micro switch which would operate on a 24 DC or AC. If it's an older machine, it would most likely be an AC circuit. The newer technology would be a DC circuit. And that being said, it would be because it has a PLC along with an inverter drive, and the old school circuit would be hardwired. Again, this would be a micro switch on here, and this micro switch would be the one that triggers our hardwired circuit. Can you get that? this hardwired circuit would control the run circuit, which is the 24-volt run circuit that disconnects and connects power going to the inverter, which energizes the motor. On a safety circuit, you do not want hands, anything inside the machine to energize the circuit. So this is done when the gate is opened. It would break the circuit and shut off all power. Nothing is energized, nothing will turn unless it's turned manually. Thanks for tuning in. I'm Charles McDaniel. That'll conclude mine.